Hello everyone, welcome to today's class. This is Teacher Simon taking you through Cambridge International AS and A-Level Chemistry Paper 2 for Feb March 2020. Question 1. Group 2 metals form alkaline solutions in water. A Roman 1, write the equation for the reaction of calcium oxide with water. Of course, when these ones, the oxides of group 2 react with water, we are going to form hydroxides. So here we are going to have calcium hydroxide. So that is the one. Is it balanced? Hydrogens are 2, oxygens are also 2, and oxygens are also 2, calcium is 1. So balanced. As simple as that. The next, Roman 2, identify the ion that causes an aqueous solution to be alkaline. Of course, that is the hydroxide ion. You can write it as the word hydroxide ion, or you can write it as a formula, okay? They said identify, but if they say name, strictly it has to be this, or the formula, it has to be that, okay? Next part, B. The table shows the melting points of some group 2 metal oxides. Explain the trend in the melting points of the oxides down the group. So what do we see? We see that the melting points are decreasing down the group, okay? But then for the melting points, we look at the structure and the bonding. All of these ones have giant structures. The bonding is ionic, okay? But then let's look at the bonding in there. What is that attraction? So as you go down the group, first of all, the size of these cations increase. As the size of the cations increase, okay, if the sizes are increasing, that simply implies that we are going to have an attraction here, which is going to be small, because now this other ion, let's say the oxide ion, okay, remember the attraction of this negative charge has to be within the between it and then the nucleus, okay, of this cation here. Now, because the length here is too big, then that simply implies that the attraction is going to be weaker. So I will say melting point decreases down the group, because of the decreasing charge density, of the cations, okay? Yes. So, by the way, the charge density, we look at the charge, then divide by the size or the ionic radius. So if something is so big, if the cation is so big, all of them are 2 plus. So you have a 2 and then a bigger value here. If you have a bigger value here, that means the whole value you are going to get out is going to be very small, okay? But if you have 2, then divide by a smaller value, then you are going to get a big value, right? So that decreasing charge density brings about the decreased attraction between the cations and the oxide ions. So our melting point decreases down the group because of the decreasing charge density of the cations. Therefore, decreased attraction. Therefore, decreased attraction between the cations and the oxide ion. You could even say that maybe lower forces of attraction between the cations and the ions. You would say that cations become larger going down the group. Therefore, lower forces of attraction between the cations and the ions. Simple. Talk about the attraction between the ions, okay, which becomes very weak down the group. Why? Because of the increasing cationic sizes. Simple as that. Then C, oxygen reacts readily with some metals, but each group 2 metal requires strong heating to start the reaction with oxygen. Okay, suggest why strong heating is required to start these reactions. Of course, that means that the activation energy is high. So we shall say heating overcomes the high activation energy. And then part D, beryllium oxide reacts with hydrochloric acid to form molecules of beryllium chloride. Deduce the bond angle of beryllium chloride. Of course, here we are going to have beryllium is first of all in position 4 of the periodic table. So it is 1s2, then 2s2. So it has 2 electrons in its outermost shell. That means it is going to share them, is going to give them out the chlorine. So since it is molecules, then this one is covalent, okay? So they share the electrons in there. So in the sharing of these electrons, we are going to see that this one will be 180 because we don't have any lone pairs. If we had lone pairs using valence shell electron pair repulsion theory, then we wouldn't be having this one as linear. So the shape here is linear, okay? And therefore the angle here has to be 180 degrees. Part E, unlike the other oxides of group 2 metals, beryllium oxide is amphoteric. Roman 1, give the meaning of the term amphoteric. This is the ability to react with both acids and bases, with both acids and bases. So that is the meaning of amphoteric. And then Roman 2, beryllium oxide and aluminium oxide have similar chemical properties. Okay, aluminium oxide is also amphoteric, just like zinc oxide, so can react with both acids and bases. Okay, now in the books we don't have the reaction of beryllium oxide with let's say sodium hydroxide or with acid, but we have that one of aluminium oxide. So now here they are saying this ion here, this anion, is a product of the reaction between beryllium oxide and excess concentrated alkali. So construct an equation for this reaction, just like the one for aluminium. So the one for aluminium, we have like aluminium oxide, okay, which is a solid, then plus sodium hydroxide, okay, and then when we add sodium hydroxide, and this is aluminium oxide, we add there water. But if it is aluminium hydroxide, okay, there we don't add water. So here we get sodium aluminate. Aluminate, we put here OH4, then aqueous here, okay, that one there. Now when we try to balance this, aluminium is 1 here, so it has to be 2 because this one is 2. Then that means sodium will also be 2 here. How about the hydrogen? Hydrogen here will be 4 times 2, that is 8. Whether this is 2, then that means we need 6 here. So I'll put a 3 on water. Okay, so I'll put a 3 on water. Oxygen becomes 3 plus 2, that is 5, then plus 3, 8. 4 times 2, 8. So that is the one there. Now, for this one here, beryllium oxide, is a product of reaction between these. So I'm going to do the same thing. This is beryllium oxide, then plus 2OH, okay, because here we have 2OH, then plus water. In fact, not 2OH. Let me first write OH, okay, then we shall add water, just like here, and then we get this berylate. This one would have been sodium berylate if this is sodium aluminate. You see that? This is 2 minus. Okay, now we can balance. if hydrogens here are 4, then I'll put a 2 here to make these 2 hydrogens and then the 2. So that one becomes 4. Okay, how about oxygen? 1, then 2 here, those are 3, then 4, and then also the charges. This is 2 minus, even this way 2 minus, so it is balanced just like that. Then part F, magnesium oxide reacts reversibly with chlorine according to this equation here. Under certain conditions, a dynamic equilibrium is established. Okay, then Roman 1, state 2 features for a reaction that is in dynamic equilibrium. Number 1, the rate of forward reaction is equal to the rate of the backward reaction. Okay, rate of forward reaction is equal to the rate of backward reaction. And then next, we shouldn't see concentrations changing. Okay, so concentrations of reactants, and products are constant. They are not equal, they are constant, meaning what reacts and gives the products the same that reacts this way, and then so it is always like that, moving in those 2 directions. Sometimes instead of writing that, you can write in a closed system. This one is the same thing. Okay. Then Roman 2, the equilibrium constant Kp is given by the following expression here. At 1 times 10 to the power 5 pascals and 500 K, 70% of the initial amount of chlorine has reacted. Calculate Kp and state its units. Now, this is how I'm going to attempt this one. First of all, we have this equation. Where is it? So magnesium oxide here, which is a solid, then plus 2 molecules of chlorine, and then here we are getting 2 moles of magnesium chloride, and then oxygen. So at first, okay, at T is equal to 0 initially, we have, we are going now to consider the gases here because we are dealing with Kp, okay? So initially, let's say we have X moles of chlorine, but then since now we are looking at the gaseous molecules, this is oxygen and this is chlorine, so that means this way we have 0 for oxygen. Okay, then at equilibrium, what are we seeing? Something reacts off from here. Okay, and I say that 70% of the initial amount has reacted. So 0.7 of X has reacted. That means it comes this side as what? The one that has reacted. Remember, this is 2. The mole ratio is 2 to 1. That means, of course, this one here is a half of this 2. So meaning what reacts off here comes this way as half of it. So it will be 0.35. 0.35 when you get this divided by 2, okay, of X. So that's what we get here. Actually, when I subtract here, this one will give me 0.3 of X. And then here we are having what? That 0.35. Now we can look for the mole fractions here. So the mole fraction of, let's say, for chlorine, okay? For chlorine, of chlorine, this one is going to be what we are having here, 0.3x, then divide by the total, 0.3x, then plus the total that we have at equilibrium. We have this, then plus that, okay? So plus 0.35 of x, okay? And of course, x is common. That means it will disappear. So let's check here. 0.3 divided by 0.3 plus 0.35. It gives us 6/13. 6/13. 13. That means that mole fraction of oxygen will be 7 over 13, because these are the two that we are looking at. Okay, if this one is 6, the other one has to be 7. Okay, then for us to get the Kp, we have to get the mole fraction, this one of oxygen. So oxygen, we are having it here as 7 over 13. That's the mole fraction. Then times the total pressure. That is how you get the partial pressure. Partial pressure of this oxygen is going to be its mole fraction, then times the total pressure. So times 1 times 10 to power 5. Then here we shall have 6 over 13 times 1 times 10 to power 5. But this one is squared if you look here. Okay. Then what do we get when we put in the calculator? We have 7 over 13, then times 1 times 10 to power 5. Then we go down, we also say 6 out of 13, then times 10 power 5. I don't need to put times 1 times whatever, that is power 5. And then I'll square the whole of this one here down. Okay, like that. When I come back here and I put a square, we shall get 91 over that, which gives us 2.53. That is to 3 significant figures times 10 to power negative 5. 2.53 times 10 to power negative 5. And then the units. For the units, you can see that up here we are having the partial pressure. Since this one is in pascals, then it is in pascals. So we have pascals, but then down here we have pascals squared. Pascals squared is the same as pascals times pascals, right? This one cancels with that. You get 1 over the pascal, which is the same as pascals power negative 1. So I can write pascals power negative 1. Part D, magnesium peroxide is made in the following reaction. This is the one here. It is an exothermic reaction. That means it gives out energy. And then we are given the table here. Then they say the peroxide ion in here is this one. Deduce the average oxidation number of oxygen in the peroxide. Now, there are 2 oxygen atoms here. So I will say 2N. Okay, we don't have any other atom. Then this one is equal to, the charge here is negative 2. Then when I divide all through by by 2, I will get a negative 1. So that means the answer here has to be negative 1. And then Roman 2, define the term enthalpy change of formation. So this is the energy change. We are looking at formation of 1 mole of a compound. Okay, this is the energy change. This is the energy change when 1 mole, very important, of a compound is formed. When 1 mole of a compound is formed from its elements, in their standard state, very important, in their standard states. And that is it. If they say standard enthalpy change of formation, then you can add on under standard conditions. Okay, so that is that. This is 1 mark from its elements in their standard, and then 1 mole of a compound is formed. Okay. Use Roman 3. Use the data given to calculate the enthalpy change of formation of magnesium peroxide. So what I will do, I'll pick this reaction here. Magnesium oxide, which is a solid, plus hydrogen peroxide, which is a liquid. Then you form magnesium peroxide, solid, then plus water, which is a liquid. Now these ones, this one here comes from magnesium, which exists as a monoatomic solid, and then oxygen exists as a diatomic molecule. Okay, but we also have this one. There is hydrogen in there, which also exists as a diatomic molecule. So we have this one here, and also this one here. So there is production of this one here. There is also formation of this one here. There is formation of magnesium peroxide. There is formation of water. So here we are forming 1 mole of magnesium oxide. That is enthalpy change of magnesium oxide. That is negative 602. Negative 602. And then for formation of the peroxide, hydrogen peroxide, that is negative 188. Negative 188. Then we also have magnesium peroxide. I think that is the one that we are looking for. Let me just label it as an X here. And then for the formation of water, we have negative 286. By the way, before you do this, you have to balance this equation. But the equation was given to us when it is balanced. Okay. All right. Now, using Hess's law, I'll take this direction. This is clockwise, then joins here. Okay, so the clockwise is equal to the anti-clockwise. Okay, and also in here, the enthalpy is negative 96. So this one here, negative 96. So meaning I'll have negative 602 plus negative 188 plus negative 96. Then is equal to the X, which is here, then plus this one here, plus negative 286. So meaning X will be equivalent to negative 602 minus 188 minus 96, then plus, because when this one crosses, it's a plus. So we shall have plus 286. And what is our answer here? Negative 602 minus 188 minus 96, then plus 286. We get our answer as negative 600. Negative 600 kilojoules per mole. Roman 4. Magnesium peroxide decomposes slowly to form magnesium oxide and oxygen. Magnesium oxide here gives off the oxygen, magnesium oxide. Magnesium peroxide gives off the magnesium oxide and then the oxygen. Use your answer in G Roman 3 and the data in the table to calculate the enthalpy change of this reaction. If you are unable to obtain the answer, we got it already. Okay, so the enthalpy change of the reaction here. Now, I'm going to do something small here. For this new reaction, we have magnesium peroxide, then which is a solid, and then gives us magnesium oxide. Then also it gives us a half here of oxygen. Now these ones are coming from magnesium as a solid, then also oxygen here as a gas, right? Okay, so I have these boxes here. So here we are forming this one. The enthalpy formation of this from its elements, we have seen that it is negative 600. Okay. Then here we are looking for the DHR. Okay. This is the one they have told us to find. Okay. Then for formation of magnesium oxide, we saw it was negative 602. Of course, for formation of oxygen, that one is an element, so it's not there. So I can also take this one here. So negative 600, then plus DHR here shall be equivalent to negative 602. So meaning DHR is going to be negative 602, then plus 600 when you make this one cross. Okay. Then what else are we going to have? Of course, this one will give us a negative what? A negative 2. So meaning our answer here is negative 2 kilojoules per mole.